Okay, go live. All right. Thank you all for joining me. Currently, let's go to the satellite live satellite feed. That's actually courtesy of right there. That's actually the ash cloud from St. Vincent. That's actually how far the ash cloud has gotten. That is very far. That's about 300 or 400 miles away. That is incredibly far. That's like 200 miles at least. There's been reports of ash falling on on Barbados. There's been ash falling there. Yeah. Yep, the ash fall likely to continue. Thunder and lightning, heavy ash falls. April 11th, that's yesterday. In the last 12 hours, episode of tremor recorded. Hours. So yep, there's ash falling in Barbados, as I mentioned. Let me go. In fact, just go to Twitter and let's look at what's happening there. Yep. This is St. Lucie, Barbados. Noon. It looks like midnight, basically. Yeah. It's dark. Can you believe that? Not only, yeah, that is absolutely insane. Jeez. It looks like it's twilight, actually. Oh my god. Looks like a thunderstorm is coming in. It's much darker than in the south of St. Vincent. Yeah, basically the southern part, that's darker than in the southern part of St. Vincent because they're right in the path of the ashfall. Like, okay. If you look at geos, let's look at this light loop. Boom, the ashfall is going right over Barbados. Literally, I was looking at the ash. There's still ash. Like, that was an explosive paroxysm right there. In fact, these clouds that you're seeing here are actually the the anvils because the volcanic eruption was powerful enough to produce its own thunderstorms, basically, because of the heat and convection from the blast. That is also from the eruption. You could actually follow the path. That's from the last eruption plume, and it's even here. Those are clouds. That's actually water vapor clouds from the eruption. That eruption occurred about an hour. Let me see. So the eruption likely occurred, 040. That's about 8:40 p.m. 10 minutes later, boom. So the eruption occurred between 8:40 and 8:45 p.m., which was about 4 hours ago. 4.5 hours ago is when the eruption occurred. That's what's left over. So it's probably still venting. There's probably still small scale explosions that were not going into the stratosphere. So in fact, let's look at volcano discovery. Discovery, La Soufriere. Yeah. $40,000 feet. Lava See, April 11th, what happened here? Close. There, April 11th. So that was earlier today. Yep. April 10th, that was 2 days ago. Well, technically yesterday in a way. So these eruptions are still continuing. These are basically not one big blast. It's kind of like pulses of these violent eruptions. Wikipedia said this is a VEI4 eruption, but I would not be surprised if this continues. It may be upgraded to VEI5 because it's pulses of eruption. So you're definitely not going to get a Plinian eruption. This is what is considered sub-Plinian. Sub-Plinian means it's not on the order of what happened in Vesuvius, or what happened at Krakatoa, Krakatoan eruption, or Pinatubo. This eruption is definitely stronger than the 1979 eruption. This eruption is actually more similar to the 1902 eruption of La Soufriere, which killed 1,000 people. This eruption, that eruption that killed 1,000 people, occurred at the same exact time that Mount Pelée erupted and wiped out the entire town of it wiped out the capital of Montserrat. It wiped it out. Sorry, not Montserrat. I'm sorry. It was Mount Pelée. It was Martinique. Saint Pierre was wiped off the map. So Martinique, the eruption was a strong VI4, maybe even a low N5. Like, it was considered a Pelian eruption. See, it was about high end VI4, low end VEI5. See, this is also considered VEI4. But the thing was, it had a climatic phase. This actually might have been a 5, considering how strong it was. And it was not one pulse and boom, it's done. It was a ongoing eruption. It was definitely a Plinian eruption. They're talking about tsunamis. The phreatic eruptions are given way to magmatic eruptions as magma reaches the surface. A tremendous explosion. Let's see. So May 5th was when let's see. The explosions resumed the night of May 5th. So the eruptions, remember, resumed on Mount Pelée 3 days. So let's see. Till 1905. Wow. On May 8th. So the thing is, the first eruption is definitely not the most powerful. It's usually in the middle to end of the eruption. A tremendous explosion, a ground-hugging cloud of incandescent lava particles. St. Pierre at 8:02 a.m. It's only 2 minutes. Wow. Escaping the city was virtually impossible. 20,000 people died. Ignited a firestorm fueled by smash. Only 2 people survived in the city. Wow. All survivors were bad. Oh, that's horrible. Jeez. Subsequent activity. Yeah, the volcanic spike. Yep, that was from the 20s, I believe. Ooh, actually, you saw a little animation there. Tiny one. See? Let's try again. There. So that is a pyroclastic flow right there. Pyroclastic flow, pyroclastic flow. ash fall, ash plume, lava bombs, magma. Yeah, these eruptions don't usually have lava flows. Well, lava, yeah. These eruptions usually, all the magma basically just vaporizes into rock. So lava dome. Yes, that's correct. And the lava dome won't be colored red. A lava dome is basically, you'd think it's a rock, but at night it might glow a little bit. And these pyroclastic flows usually happen when the lava dome collapses, or the pressure releases, and you get a gigantic explosive eruption. What is happening in right now in St. Vincent is, while the lava dome is surrounded by higher terrain because it's in a caldera, in a crater, the issue is there's a lot of pressure, so there's a lot of material being thrown out. So even that's the problem. With St. Vincent, there's just too much pressure. Even though the lava dome is encased in the crater, there's so much pressure that there's basically a ash column, and when the ash column collapses, you can get very strong pyroclastic flows. So an ash plume or ash column, especially if it's suspended by heat, by basically by thermal forces, once the volcanic eruption weakens, the thermal heating that's keeping the ash plume suspended will weaken. The ash plume will collapse, but the ash plume is still superheated. And once the ash plume, once the interior of the ash plume becomes cooler than the surrounding areas, even if the outer part of the ash plume is still really hot, it collapses and you get a pyroclastic flow, or a base, not like a base surge. You get a really fast moving pyroclastic flow. Yeah. What is happening at St. Vincent is not a Pleiadian eruption. It is a subplinian eruption. So let's look at the satellite again. Let's look at Twitter. Let's look at latest news from Barbados. Okay, let's see. Yeah.
As you can see, this is the beach.
Yeah, covered.
There's no sand.
All colored ash.
And you can see the water's very mucky and brown.
Well, okay, that's seaweed right there. That's seaweed. That's ash. And it's not a lightly colored ash. It's a dark colored ash. Darker colored ash means it doesn't have as much gas in it, so it's not that so that's a good sign. If the ash was lighter in color, that means it's has more air in it, and it's cooler. So this is definitely fresh magma, which means I don't think the eruption will be that much more explosive.
Show you how it's really looking. These are the plants, right?
Yeah, that's actually pulverized rock. That's not dust. Ash is actually
dust is on them from the ash.
Pulverized rock.
Even though it rained. This is how it is. Yes, Agenda TV. I just want to show you how it's really looking. These are the plants, right?
Yeah, you should not be outside.
That's how much dust is on them from the ash.
Yeah, that's old. That's a very old video. This video's from this video I really watched it was earlier today. No, that's actually not ash. The red, that's actually Here's the thing: ash is not. That's actually convection. That's actually cold cloud tabs. That's actually all cloud. There's ash in that, definitely. There's ash in that, but that's actually cloud tops, by the way. Jeez. Yeah, but don't throw that out. That's actually very useful for your plants. Ash is actually a very good fertilizer. Has a lot of phosphorus and very impressive, very good nutrients. That's why Italy has such good vineyards, especially around Etna. Very, very important. Yeah. Ash is a very good fertilizer. Natural fertilizer, doesn't harm the environment. If you use it, you know.
Then I leave and go
That's St. Vincent. Georgetown is Barbados, but this is St. Vincent, actually.
And I see other old men around at them times. So I feel I could step this time.
Yeah, this is definitely St. Vincent. That looks like about a quarter of an inch of ash. Not a lot, but still, it's making everything very difficult. Cars are having issues with traction. It's even caused water outages and power outages. Yeah, people are even losing access to water. This is really bad. And let's look at let's look at let's go back. Let's look at animation loop. Boom. So see, when it erupted, you had a very strong cold cloud tops. It's also ash plume, or what was left of it. That's now it's cloud. Ash clouds are never cold. Ash clouds are usually very warm. Ash itself doesn't register on these satellites. It's the clouds that do. Because when you have this eruption, big plume of hot ash going up, hitting the cold atmosphere, you're going to have a lot of condensation and thunderstorms. Yeah, volcanoes also form their own thunderstorms. It's not just dirty lightning. I mean thunderstorms that produce rain. Pyrocumulonimbus. That was a giant pyrocumulonimbus right there. Of course, it probably dissipated like somewhere like 20-30 miles out to sea. But the thing is, that's why it wasn't just raining ash, it was raining mud, because these thunderstorms formed by these ash fall, by this eruption is forming, you're having not just ash fall, but rain mixed with ash. It's mud. And you're also getting pumice. I know somebody who lives in St. Vincent, or somebody who has family in St. Vincent. They said even on the southern end of St. Vincent, there was reporting falling rocks yesterday, on the 10th. There was pumice falling down in the southern part of St. Vincent. That is incredible. Now we're going to be changing gears, and we're going to be talking about Campi Flegrei. So this is the seismogram. Here, actually, let's see if there's any activity today. Not sure that was an actual quake. Let me see. Yep, looks like that was a small quake. Very small. Let's go home. Campi Flegrei. Let's look at seismological. Let's look at earthquakes. Anything today? No, they didn't register anything, even though there was an earthquake there. .3. Actually, the strongest quake was a 3.3 on April 26th. They're probably going to reset it because this is the past year. See? So all that's going to dissipate. And that's the big earthquake storm that happened on April 26th. It wasn't a 3.1, it was a 3.3. And I yesterday edited a Wikipedia article on Campiflegrei, especially on the uplift. I had issues linking this site, even though it's in English. That's because it's through Google, it's translated. So I had to link it to the Italian link for Campiflegrei, and then I had to link the English Wikipedia to the Italian one. I mean, I had to link the Italian one to the English one, so people on the English one could go to the Italian one to look at the data. Of course, you'll probably need to translate it, but yeah. So let's look at the bulletin for April 6th, which is just look. So basically, there was 72.5 centimeters of uplift since January 2011. Strongest tremor was a magnitude 2.2 from March 29th or April 4th. So yeah, so this is the update Bollettino Settimani, which means Settimani means basically so emission, including emissions data on the 6th of April 2021. And emissions data is right here, and actually showing a decrease in emissions. There's actually, since 2020, there's been a significant decrease in emissions. Going back 3 years, carbon dioxide emissions have actually been decreasing slightly. I mean, you had an increase in from January through about August. So January, yeah, Lug, I think it's Lug is July. Lug, July. See, yeah, July basically. Lug means you like July. Yeah, that's what I thought. It was probably July. They had an increase and then a sudden sharp decrease in uplift and emissions around July. But here's the thing: if you look uplift around the same time, it actually increased. You didn't have a decrease in uplift. Uplift is increasing, which means the volcano is pressurizing. Here's the thing. Here's the thing, basically. Where do we had a big increase in 2020 right here, see? You had a large increase right around January. Jen. Right here. So January 2020 had a big increase of emissions, and that correlates with a slightly slower rise of ground deformation. Why? Because what's causing the uplift isn't magma, it's gases that are rising in the caldera. Not hydrothermal gases, magmatic gases. This uplift is caused by the volcano pressurizing. The more gas that builds up, if this continues dropping, you're going to have a much faster rate of increase, and then eventually the whole thing is going to go off. You're going to have a massive eruption at Campiflegrei. Unless CO2 emissions rapidly increase, and it outgases faster, the volcano can depressurize and avoid an eruption. The issue is it's these gases that are really, really dangerous. In fact, see? As if yeah. Where is it? Oh, yeah. You see that? You see that? Oh, that gas that is rising up right now. Man, that is bad. Yeah. Basically, going on more than 2 kilometers deep, just gas and gas and gas and gas. They're saying, Mount Vesuvius is not even 2 kilometers tall. They're saying that this magma plume is taller than Vesuvius, and it extends only 300 meters down below the surface. That's really shallow. That's like, what, 700 feet? That is really shallow. And there's also magma in this area too. They found the presence of magma really shallow. So basically where the gas ends, that's basically where the magma ends. So there's a lot of gas-rich magma rising up. I don't think that's meteoric water, because there's a shallow magma chamber under the caldera here too. So, but basically it's the gas that's the biggest problem with volcanoes. You know, Hawaii has almost no gas. It's basalt. Gases can easily bubble out of solution. So it's easier for the gases to escape, which is why it's mostly non-explosive. The only time you may get an explosive eruption is if you get magma mixing with groundwater, which causes a sudden change in temperature, which can generate a steam-driven blast, or a phreatic or hydromagmatic eruption, or phreatomagmatic. People think that the cause of the big explosion at Santorini, the VI-7, was a hydromagmatic or a phreatomagmatic eruption. I actually believe that what caused the really explosive phase of the eruption, like what happened at Krakatoa, was the mixing of magmas. Hotter magmas, from down below mixing with cooler magmas in the caldera, in the magma chamber, and basically overpressurized the volcano, and it just had a massive eruption. Same thing with Krakatoa, that big blast that everyone heard, that was heard from 3,000 miles away. They determined it had nothing to do with the interaction of water, that in fact it was the pressure that was inside the volcano. They determined that it was in fact the gases in the volcano exploding, because the eruption happened in phases, and then you had tsunamis from pyroclastic flows, because the flows were so intense. There was so much debris spilling off the sides of the volcano that it generated massive tsunami. In fact, Krakatoa had a bigger eruption, according to legends, in the 400 or 500 AD. There was a massive eruption which formed the islands of Lang and Verbatim in the Sunda Strait. That could be the reason why, you had a very bad year in 535 to 536 AD, why there was a global cooling event. Also, there's some other possibility that there was an asteroid impact in Greenland, but that's more unlikely, or in the ocean. But more likely it was a volcanic eruption, because they found high presence of sulfur in the Arctic, which indicates that it was likely a volcanic eruption, and a very strong one at that. It's not the only one. Ilopango erupted in the 400s, 435, 436 AD, but nothing significant happened at that time. The significant stuff happened in the 500s, not the 400s. So Ilopango, while it was deemed the cause, it's actually not. It's likely either Krakatoa or some other unknown volcano in the 500s. But we do know that in the 540s there was a very, very strong eruption in Iceland that definitely could be blamed for why Europe had such a bad year. In fact, the 535-536 year, the year where tree ring data from all around the world that showed a significant drop in global temperatures. And yeah. Microseismicity? Okay. The filigrane field. Increase in temperature. Among the parameters analyzed is the diffuse flow of carbon. This is translated. This article is actually normally in Italian. So I'm saying, Among the parameters analyzed is the diffuse flow of carbon dioxide from the area's soils. The processing shows an increase in the amount of CO2 emitted, which from 1,500 tons per day in the period before 2017 to about 3,500 tons per day in the following period. The variation in carbon dioxide emissions is simultaneous with the increase in seismicity. Okay, so basically, yeah, it's caused by, yeah. So basically, yeah. We continue reading. Furthermore, most of the hypocenters of the small earthquakes occurred in the superficial part of a vertical structure, which was identified using magnetotelluric techniques. The structure has been interpreted as a plume of gas. You can't see gas? Are you kidding me? The same that feeds the flow of CO2 measured in the soils of the Solfatara, and which has been subject to the increase in the estimated pressure and temperature. Okay, pressure is increasing, temperature is increasing. It's not just more gas, it's magma rising. The gases are causing magma to rise. The coincidence, both temporal and spatial, suggested to the researchers that the observed variations caused by pressurization, I agree with that, of the structure present in the subsurface of the Solfatara. Absolutely, yes. I just read it wrong. The novelties of the study, continues Cialdini, are the collections of the enormous amount of multidisciplinary data, most of which are really public, and the use of a statistical technique. The principal. Alright, the study highlighted that the observed variations find their common case in the increase in fluid pressure. Yep. Civil, no immediate implications for civil protection aspects. Okay, they're saying that basically, that while there's increasing gas and pressure, that's no threat. Here's the thing about Campi Flegrei. Let's look at the rate of uplift in this volcano. Okay. Do you see this right here? Let's look here. 13 plus or minus millimeters per month, which is averaged in September 2020. So, in the last 6 months, average of 13 plus or minus. So let's go to last month's update, all right? See what they're saying. And what they're saying is 72 centimeters since January 2011. Well, let's go all the way back to January 5th, when I was still obsessing over it, by the way. Oh, and now they're saying how much? Oh, 2.6. 6 millimeters a month. Okay. since January 2011. Okay, this is from December, like end of December. 68 centimeters a month. A patrie. Yeah, since January 2011, there's been 68 centimeters of uplift. Now let's go to January 5th. 68 centimeters, and now, bulletin for April 6th, 72.5. So let's go to September. Let's go all the way back to September, just this September, right? September 1st, 2020. 115 degrees Celsius, that's pretty hot. 64 centimeters. And let's go to April, which is about half a year. That is 72.5 centimeters. So basically an increase of 8.5 centimeters in only what amounts to about 7 months. Just basically 7 months got 8 centimeters of uplift. So the rate is pretty accurate, 13. December 2020, about 13. Let's see how that adds up. Let's see, calculator app. 8.5. Divide that by basically 7. Multiply that by 10. Well, 12.14. It's about 12 millimeters a month. But here's the thing. And it's going to be 8.5 divided by 7. Or is it? Yeah. Let's go to the 1st of September, right? Just want to make sure that it all correct. 64 centimeters. And then from October, 65 centimeters. So 65 centimeters. That's 7.5 divided by 6. Times, multiply that by 10. About 12.5 centimeters. So yeah, 12.5 millimeters per month. Let's do that by year. That's 150, so that's about, divide that by 10, that's 15. If it were at that rate, that would be 15 centimeters per year. But of course, we're not getting, that's not the average for the whole year, that's just the average right now. But usually, the rate was right around 100. See, 200, 2020, 100. So the rate has almost always been consistent at about 100 millimeters a month of 100 millimeters a year of uplift. But now the rate is increasing. It's been increasing since about late 2020. The rate started increasing right around since January, February, March, April, May, June, July. So the rate of increase started right around January, February, March, April, May, June, July, August. So right around from August is when it started increasing, which correlates to let's see, make sure I'm reading the graph correctly, to a decrease, a decrease in CO2 emissions. This is grams, so there was a pretty large decrease in CO2. That is about CO2 grams per meters. Yeah, that's flux. That's CO2 flux, basically. Yeah. grams per meter. Yeah. So that's a pretty large decrease. That's a lot of pressurization. But that's one station. St. Vincent volcano, while it's dangerous for the locals, this volcano can have worldwide implications. And this volcano, if it erupts unexpectedly with its full potential, it can definitely kill millions because, you know, I'm saying if it erupts without warning. It's like it just, boom, overnight has a mega ultra plinian eruption, which is very, very unlikely. I mean, the Roman town of Baia is still underwater. And the thing is about Baia sunk under the ocean between the 3rd and 8th century AD. Like, yeah, the Roman villa, some of it are still underwater, sank around the 3rd to 8th century AD. Now that the uplift is starting up again, it may be a few more years before all of Baia re-emerges out of the water. There's still the port of Baia, which is still under the water. See? But the thing is that the center of the uplift is centered around Campi Flegrei, or Pozzuoli. See, opens at 9 a.m. Okay. So right in the same location, basically. So you see, very close. So the center of uplift is right in this area. So this is the caldera right about here. This is basically the caldera here. But here's the thing. Vesuvius and Campi Flegrei share one large magma chamber. This is basically one large volcano. This Naples is between those two volcanoes. Yeah, I wouldn't be surprised if a volcano decides to prop up right under Naples, because both volcanoes share one magma chamber. Vesuvius only started forming 25,000 years ago. This is actually a new volcano. This Vesuvius, the one that everyone knows about, is actually Campi Flegrei's offspring, basically. This is the daddy, this is the son. Yeah, basically. They share one large magma chamber. They may not share the same magma chamber locally, but they share the larger one underground. Just like Cinnabung shares one large magma chamber with, well, Toba. Very likely, because they analyze it and they have the same ash. The same ash. A completely separate volcano has the same chemical properties, indicative that they share the same chamber. Having one common chamber, like basically, after because of the cap rock that formed after the second flagrant eruption, which happened 15,000 years ago. But the thing is, this volcano started forming 25,000 years ago, while the second flagrant period started about 30,000 years ago with the Neapolitan yellow tuff eruption, also a VI7, 6 to 7, happening around 15,000 years ago. So the thing is, the Neapolitan yellow tuff. Oops. Oh, great. Okay. NYT. Can be from Great Caldera. So about 15 to 14 and a half, between 15,000 and a half to 14,000 and a half years ago. Basically, you could say 15,000 years ago. Plus or minus half a thousand years. Ferratoplinian. So basically, this is the yellow tuff. This is the welded tuff, basically. So pyroclastic flows. This is all pyroclastic flows. We're reaching out. So yeah, Naples was completely demolished, gone. Surprisingly, it says it didn't reach Vesuvius, which I don't believe. So the caldera from the eruption 15,000 years ago. So all of Pozzuoli Bay is one big caldera. I used to think this was one big caldera too. I mean, it kind of looks like one, if you think about it. I mean, Yellowstone is a bigger caldera than this, so... But the thing is, this could be a natural bay. Well, this is a caldera. But Campi Flegrei is not only a caldera, it is a caldera and a volcanic field. Both. It's dual caldera and a volcanic field. See the smaller craters? But it is a caldera. But it's not a supervolcano. Because the thing is, in order to be considered a supervolcano, it has to erupt 1,000 cubic kilometers of ash, lava, and rock, all in the same eruption. Thing is, its largest eruption was about 300 to 400 cubic kilometers. Not a super volcano. Sorry, Campi Flegrei is not a super volcano. It is a powerful volcano, but it's not a super volcano. Sorry to burst your bubble, guys. It's not a super volcano. Even though it is a caldera, it could one day have a super volcanic eruption. It could, but in the distant future. It might one day. I don't know. It could one day possibly have an 8 if it doesn't erupt for hundreds of years, if it continues to uplift, and then, yeah. But the center of uplift right now is centered right in this area here, which is basically the center of the caldera. But you see, that's Monte Nuovo right there. And get the center of uplift. Eruption volume. Actually, let's go to YouTube. There was this really good video. Yeah, it's my channel. Like, I'm looking for an actual document, not a... There we go. This is what I was looking for.
Layer where the water can accumulate, producing a lake. So that's the way calderas form. And if... Thanks a lot, and good...
Paolo Papali. Yeah, I really like Paolo. He's no longer in charge of INGV. It's actually a woman right now. I forgot her name.
Morning, everybody, and I wish to thank Carlo for of conditions, but we select many, each one associated with its probability. So we have a vent from here with its will be an eruption following. At the beginning of the 80s, a large rise of the ground, and then again subsidence, and we'll see where we are today. So from the 60s on, something new, from the 50s on.
Yeah, we're like somewhere over here right now. We're definitely uplifted quite a bit. We uplifted like... We're somewhere like, I'm gonna say, almost up to this level.
Oh, sorry, something new has occurred at Campi Flegrei. Campi Flegrei are today a volcano in an unrest phase. Something is happening here that we need to understand in order to try to forecast the possible occurrence of the next eruption.
Yeah, you should subscribe to the...
I told you that this point is the sea level...
Yeah, I really like the European Geosciences Union. They're amazing. I really enjoy watching their videos, especially on volcanic activity.
This point here was below sea level.
Please subscribe.
And that subsidence dominated since the Roman times. And we can see that because in front of Pozzuoli, this is Pozzuoli in the center of Campi Flegrei, and we can see here the remnants of villas from the ancient Romans, which are 2J below the sea level, because, well, this point in ancient times was up here, above the ground, and then it went down, 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 until it was submerged. It was below the sea level. This is the Sierra Pio Temple. It's very famous. It's an ancient Roman market, and it's located in Pozzuoli, close to the harbor of Pozzuoli. This is a picture from the 50s. Water. This point here is, in fact, a point in the Sierra Pio floor. Okay, so the Sierra Pio floor was submerged in the 50s, and you can see here it was invaded by the sea, and this is the same picture taken today, well, a few years ago, here, when the Sierra Pio Temple was completely out of the sea level. So really huge movements occurring, and this is about 70 years of unrest which are going on at Campi Flegrei, with a total uplift of the ground of 3.5 meters. So if one guy from the 1930 or 1940 should come there and look at Campi Flegrei, it will find that rising up of 3.5 meters. It wouldn't recognize the coastline. It's very much different from there. And of course, these movements, this uplift, cause a lot of damages. And this is a picture from summer 1983, summer 1984. From 1982, 1984, there was the last big rise of the big uplift of the floor that I was showing you, and many buildings were seriously damaged by that. In fact, there was a big concern that a new eruption may occur at that time, but there was also a big concern because thousands and thousands of earthquakes and big ground uplift were seriously damaging the buildings, and 40,000 people were taken away. And
keep in mind that last April, the 3.3 earthquake that occurred was even stronger than what happened in that period, because it was around the same time. There was like a 3.4, so this is the strongest earthquake that occurred in April 26, 2020. It was the strongest quake dating back to this episode. Yeah, it was crazy.
Relocated somewhere else. And this is again just to show you the dominant subsidence since the Roman time. This is the largest picture of the Roman...
Even though there's uplift right now, compared to the Roman times, it's still dominantly lower.
Villas, and if you go down here and dive, you can see stuff like this. These are the Roman villas which are today below the sea. It's beautiful. Huh?
Yep. And because they were built with
It's not a
pozzolana,
small
they're very
Pompeii.
strong. Actually, pozzolana is actually strengthened by seawater.
Again, so coming back,
I think Portland ash is a horrible building stuff for seawalls. I think seawalls should be built with volcanic ash because they will not only withstand the sea, they will actually be strengthened by it.
to what Campi Flegrei are doing, what kind of signals they are giving us. This is the 82-84 crisis, which is concentrated here, and this is what happened up to 2008. I will show you the rest of the story in a moment. So what we see that the red blocks here are the number of earthquakes. Okay, so we see that we have earthquakes at Campi Flegrei. We had earthquakes only at specific times when there was big uprise. The blue line is the caldera, is the floor, is the position of the floor. So it's the uplift. This is the big uplift in the 80s, and then everything went down, and there were small uprises here, another one here, another one here, and every time the terrain goes up, there are new earthquakes occurring. And also there are other signals, which are the dots and the green line, which is the composition of the gas which is ejected, which is emitted from Solfatara crater. This composition is expressed here as the ratio between carbon dioxide and water in the volcanic gases. And we see that when we have uplift of the ground, we have earthquakes and a large increase of the amount of carbon dioxide in the gases. Then decrease, then we have earthquakes, uplift, and large, and again increase of carbon dioxide, and again and again. So clearly the volcano is telling us something. The volcano is speaking. There are signals that we interpret. I don't get into the interpretation and the physics and the models that lie behind all these, but you can imagine how many investigations, how many studies, how many models have been constructed based on that in order to try to understand what's really going on at depth at Campi Flegrei. And this is the entire story up to today, practically today, of the formation. So we had a big uprise here, then subsidence for many years, but then after, with the new millennium, something new happened. There is a new trend going on now. We are not subsiding anymore, but we are rising up with a trend which is very different from what we observed in the past. We observed very large uprise here, very restricted in time, but high rate uplift here, here, here. Now we have a lower uplift rate, which is continuous in time, going on and on and on, and a bit increasing in rate. You see the curve is going a bit like this. So this is a new trend in the formation. And again, it's giving us troubles because we have to understand.
Let's pause right there. Let's continue looking at it. And let's look at the long term. And he's talking about here. And look at that. Continues. And it's really intensifying now.
What that means. This is a satellite pictures again showing the formation at Campi Flegrei, uplift at Campi Flegrei. This is Pozzuoli, this is Campi Flegrei, and the different colors here show different magnitudes
green
of the uplift. So we can see that the uplift is maximum in the middle of the caldera, which corresponds to the Pozzuoli area, and then there is a lower uplift here, here, and here. So the entire caldera is going up like this. And out of the caldera, the green area, we don't have any ground movements. So it's the caldera which is going up and up. Okay, so this is
so the entire caldera is basically uplifting.
Sorry.
Well, not the entire caldera, parts of it. No uplift here, so it's more localized. But I don't know how it's
Images. They are radar images made with a satellite. This is a principle which is based on interferometry. Those of you who know interferometry may understand how it works. There is a satellite sending a radar signal, and it goes over the same place after about 15 days. There is a new signal there. If the ground moved, the signal which is coming back is no more in phase with the old signal. There is a phase, a display in the phase. So, oops, sorry. Yep, I was joking with this. There is a display in the phase, and you can play with that and make interferometric pictures and understand how large is the phase shift and how that translates in terms of ground movement. That's the principle of INSA. And this is what I was saying, that the coastal line has changed significantly. In red here we see the coastal line before the 50s, and in orange we have the beach before the 50s. And everything we see here is come out of the sea from the 50s to today. So it's a place which is really rising out of the sea. Okay, of course we need to understand what's going on down there, and we make a lot of investigation in order to do this, really a lot. New investigation, which is again based on seismic tomography with different techniques. This is seismic attenuation. There is a T, too much T here. Attenuation, seismic attenuation tomography. With this method, we go and see how the seismic waves are damping down from place to place. It's a different technique which allows to put in evidence better areas where fluids are hosted. So we can see what's the structure of gases, what is distribution of gases and water below the Campifragre. But also with this technique here, we could identify what we think is probably magma at a lower depth of only 3 to 4 kilometers. So a large melt zone here, probably magma sitting at 3 to 4 kilometers right below Pozzuoli in the center of the caldera. And this might have been responsible for the unrest that we are observing, for the large uplift of the ground since the 50s. Everything is may, because we don't have any certainty about that. There are only hypotheses, models, and that we continuously test. Okay, so from all of that, a picture comes out like in this cartoon, where we might have a magma chamber at about 8 kilometers depth, a very large magma chamber actually, and a sill intrusion at about 3 to 4 kilometers of depth below Campifragre, below Pozzuoli. That's the picture that many people believe it's true. Many others question that. It's not universally accepted, of course, but I would say that most people now believe that's the case. And we can work with that. We can transform this cartoon here into a simplified picture that we can use for numerical simulation, for investigate what kind of processes might occur if the system would be like this one. And this is a simple schematization which is adequate for doing numerical simulations. Here we have a large magma chamber at about 8 kilometers depth, down to 9, which is hosting a volatile rich magma. Volatiles are very, very critical in volcanic eruption, as you know, because it's the volcanic gases that cause the magma to rise and produce eruptions. So, and the kind of processes in magmas is such that if you have magma coming up here, this magma will unavoidably become depleted in gases in time. So we have an intrusion here at 3 kilometers which hosts magma which is depleted in gases, and volatile gas-rich magma sitting down there, and they are somehow connected. That's a simple scheme, and we can use that for numerical simulations. What we are looking at here is a zoom in this area. We simulate the entire system, of course, but in order to see what happens here, I just make a zoom of this area here. So this is a shallow magma chamber. This is what we call a dike. The dike is connecting the shallow chamber with a bigger chamber, and there is gas-rich magma sitting here. So what happens in time is something like this. This is again solution of equations describing the physics of the system, and we can investigate how the process goes on, the process of rejuvenation of a magma chamber by volatile rich magmas. Okay, so what we see here is plumes of volatile rich magma getting into the chamber. The time is very much accelerated here. Since when we started speaking, nearly 2 hours have passed by of real time, of course. So we are accelerating time in order to see what's going on. And we can see that if the situation will be like this one, probably this is the kind of processes that may occur in the chamber. Can we see that in signals? Do we have some hints that may tell us that this is really going on? And that's not a part of the story. That's what we need to understand. So we can move from magma dynamics to ground movements. We can take all the forces which are generated on the boundaries of the system because of this process of convection going on. We have convection, mixing of magma movements. These are causing forces distributed here. We calculate those forces. We simulate the transmission of those forces into the rock system, and we see what kind of movements we might have on the ground. So we can see what kind of signals we might have on the ground. If this process would be true, we would see something like that. Do we see that? We can go back to the field and compare our synthetic signal with the real signal and see whether there are similarities or there are no similarities. And in this specific case, as you can see, the blue lines is the computed ground displacement, the black lines is what we observe, and there are good similarities. So there are reasons to believe that we have something like this below Campifer Gray. We have a shallow chamber which is periodically rejuvenated. Yeah, so we can do a lot. We have a lot of science to put in there, and the volcano observatories are today very high-tech places where a huge number of signals are continuously recorded, analyzed, very, very high-tech systems. All volcanoes are covered with instruments, but still uncertainties dominate. Still we don't know what's going to happen. And this is an example from Rabaul caldera in Papua New Guinea. Okay, this is also a caldera, a big caldera, as you can see here. This is sea, invaded by the sea. And in the 90s, in 1994, there was an eruption in this caldera. But let us see the history of this eruption. What happened is that starting from the 70s, the ground was uplifting more and more. And in the 80s, it was uplifting very fast and a lot. So the people were very scared, also because there were the blue lines here is the number of earthquakes. There were a lot of earthquakes in correspondence with these huge ground uplift, and there were not small earthquakes. There were large earthquakes, larger than magnitude 7. You've seen yesterday that magnitude 7 is a big earthquake, and nothing happens. Many people flee. Many people escaped from the area spontaneously. They went away from the cities there, but then nothing happened. So they came back and they stayed there. The ground was not uplifting anymore. It was continuously uplifting, but certainly nothing comparable to all of these, and nothing comparable to these. There were nearly no earthquakes until when small uplift here in a short time. Small earthquakes, magnitude 5, not magnitude 7, 100 times smaller than these, more or less, and suddenly an eruption occurred. So, once again, this is what calderas do. You can see a lot of signals, you can see big changes, but then nothing happens. and then you see nearly nothing compared to what you already saw, and then eruption comes. And that's the big problem with calderas. I put here the history of deformation at Campi Flegrei, which is not in scale, of course, but just to show that in Campi Flegrei also we saw in 82, 84 a big uplift, and then subsidence in this case, and then now we are sitting here. We are sitting in a place where we have small ground uplift. It's not very different from this one. So who knows what's going to happen. That's the case. And just to tell you, just to show you how complex can be the calderas, this is another example from Okmok, Aleutian Arc. This is in Alaska, okay? And again, we have these lines here show again the position of the ground. Periods with inflation, uprise of the ground, then nothing happens, stasis, eruption. Big inflation again, then nothing happens, everyone will be scared here, no scared here, instead the eruption comes after. I should quit. Just other examples, and just to tell you, well, this is an example mixing up many calderas, and you can see here that calderas, they can get into an eruption following many different trends. This is the intensity of indicators. How big are the things that we are observing? And we have everything. Even cases where an eruption follows a period where everything was slowing down and down, was smoothing down and down. We didn't observe nearly anything, and then an eruption started. And these are all cases when an eruption occurred. These are all cases of unrest at calderas where nothing happened. And again, the trends are superimposing one to the other. So we don't have any clear clue to understand what's going on with calderas. Forecasts of calderas are characterized by big uncertainties, and that's why we are talking a lot of uncertainties and relying on probability estimates instead of relying on predictions that we are not. We should still sit here when an eruption comes and cause death because of respiratory problems, and they can also cause collapse of the roofs, as I told you. And this is pyroclastic flows. I hope it works. This is pyroclastic flows formed. Yes, that's good. Formed in Montserrat. Problems, and 40 kilometers. Tubo in the Philippines. Lava flows from a very famous Etna volcano in Sicily. This is instead an eruption like this one. This is Pinatubo in the Philippines in 1991. This is the largest volcanic eruption of the last century. And this column here reached nearly 40 kilometers into the stratosphere, okay, like this one. And you can see the effects of the accumulation of ashes on the ground. So ashes accumulated on the ground that can completely shut off any kind of human activity in the territory and cause death because of respiratory problems, and they can also cause collapse of the roofs, as I told. Smaller eruption, we have seen many craters inside a large depression of the caldera, and those eruptions can be much smaller. So if we go back here, this is Tambora is 50 cubic kilometers, this is 300 cubic kilometers. Most of the eruptions, well, all of the eruptions of the last 5,000 years of activity at Campi Flegrei are less than 1 cubic kilometer. But an eruption like this one, which is the largest eruption of the last 5,000 years at Campi Flegrei, the Agnano Montespina eruption, this one will be a complete disaster. That's still quite big. It's as big as the Mount St. Helens eruption, apart from the fact that Mount St. Helens is in a remote area, there is nothing around that, while here we are in a city, in Naples, and we'll see that in a few moments. And this is the last eruption at Campi Flegrei, the Monte Nuovo eruption, which occurred in AD 1538. A very small eruption, as you can see, but still an eruption like this one will be a real problem in the area, and that's because 500,000 people live inside the volcano, live inside Campi Flegrei. You can see here from this picture, this is all Campi Flegrei, and Campi Flegrei are bigger than that, and the same city of Naples is sitting inside. A large part of the city, not all the city, is sitting inside Campi Flegrei. Okay, and this is Pozzuoli city, which is also very large. This is the Monte Nuovo eruption, the last eruption in 1538. You can see here it produced this new mountain. Monte Nuovo means new mountain, exactly that. And you can see how urbanized is the area around that. This is a picture showing the eruption in the 16th century. Still there were houses, towns, not the situation as today, of course. In fact, all the area here is heavily urbanized. There are about 3 million people exposed to volcanic hazard from 3 major active volcanoes, which are Campi Flegrei here, a caldera, Vesuvius, very famous Vesuvius volcano, and Ischia Island, which is also an active volcano, which erupted last time in medieval times. Okay, so it's 3 active, dangerous volcanoes and 3 million people living there, with a density of urbanization, which in many places is comparable to that of Hong Kong. So it's really a huge problem. It's probably the highest risk, volcanic risk situation in the world. What are those kinds of hazards that are expected when you have a volcanic eruption? Well, a volcanic eruption is different from an earthquake and from a tornado, because the kinds of processes producing hazard and risk are very many and very different. You might have a lava flow eruption. You can see here depicted some lava flows, and that is a problem, but this is certainly the lowest risky kind of volcanic activity, because lava flows are slow and you can just go away while they are coming. They destroy everything, of course, they very rarely kill people. But if you have an explosive eruption like the one that we see here, instead of having lava flows, you have a mixture of gas and fragmented magma. The fragmented death out of ash is found. Well, getting back to Campi Flegrei, this is the eruption which caused the... That's the situation of Naples and Vesuvius today. So if we had 5,000, 6,000 people who died here, now we have millions of people who live here. And this is Naples, and on the other side we have Campi Flegrei. And you can understand how big is the problem in this area. This is a completely urbanized, industrialized areas, large industries, and many people living there. Getting back to Campi Flegrei, this is the eruption which caused the first formation of the caldera, the Campanian Ignimbrite eruption 39,000 years ago that I already told you. And this is the area where fallout of ash is found today. The red dots are all places where we can find in the field deposits from the fallout of volcanic ash from the volcanic clouds. And you can see how large is this area. Okay, this is Europe and this is Russia. We are in Russia, this is Greece and whatever. So an impact which is really huge. And once again, here in yellow, this is Campi Flegrei. Here we are looking at the Campanian region. Naples is here. This is Vesuvius, Campi Flegrei, Ischia. And in yellow we have the deposits of the Pyroclastic Flows, and this is about 120 kilometers. All the major cities in the Campanian region, Benevento, Avellino, Caserta, Napoli, of course, which is here, Salerno, would be reached by Pyroclastic Flows if an eruption like that one should occur in the future. So you can imagine how big will be the destruction. And that's not the only big eruption which occurred at Campi Flegrei, because 15,000 years ago, another large caldera in the future.
Okay, so this is Pyroclastic Flows. So this is ash right here. This is all heavy ash fall. That is okay. 15. This is, of course, in millimeters or centimeters. Sorry. That is a lot of ash. That is about. Let me see, about 50, 60, like 70 miles east. That's pretty far.
So you can imagine how big will be the destruction. And that's not the only big eruption which occurred at Campi Flegrei, because 15,000 years ago, another large caldera-forming eruption producing huge pyroclastic flows formed, and that's the Yellow Tuff eruption. This is the Yellow Tuff in Naples. These are the deposits from one single eruption. One single eruption produced all these. So you didn't have that, and a few days after that, you have the city which is gone, completely covered by tens and tens, up to more than 100 meters of material produced by a volcanic eruption. So that's what we're talking about. And that's Campi Flegrei and La Solfatara crater that I already showed you. Campi Flegrei, they are an active volcano. There is a huge emission of volcanic gases occurring there. Most of that comes out from La Solfatara and another place which is very near, very close to Solfatara, which is called Pisciarelli. Those are the two areas where the gases come out with the greatest energy at Campi Flegrei. And that creates another source of problems, because gases escaping from the ground, as long as they can escape, everything is fine, everything is okay. But if instead, for some reason, the ground is sealed so that the gases cannot escape anymore, pressure can accumulate below the ground, and a phreatic explosion like this one, this is not Campi Flegrei, fortunately, but a phreatic explosion like this one may occur. And that's very, very dangerous, because phreatic explosions, they are a very superficial process, very shallow process, and they are very, very difficult to predict, to anticipate. In fact, most of the volcanologists go around on volcanoes, they die because of phreatic explosions, because they are nearly impossible to anticipate. And that's also a problem. And you can see here the magnitude of the energy which is released at Campi Flegrei through the escaping gases. This is a thermal image of Campi Flegrei. In red you can see the hottest parts of the Solfatara crater here. And this is instead the area where the carbon dioxide flux is greater. This is La Solfatara and this is Pisciarelli that I was mentioning you. There are about 2,000 tons per day of carbon dioxide which is released by Campi Flegrei. The amount of carbon dioxide which is released only by Campi Flegrei is larger than the total amount of carbon dioxide released by the volcanic Iceland, by the entire Iceland, which is entirely volcanic. But the carbon dioxide which comes out from here is larger than that. And this corresponds to about 100 megawatt of thermal energy, which will be a large a large energy plant. 100 megawatt is relatively large. And you can see here the temperature of the aquifer, which can go up to 90 degrees, but certainly the temperatures can be larger than that. And in the Pisciarelli area here, we measure up to 120 degrees in the gases. Okay. So going back to volcanic ash, what we call isopachs, they are lines. They represent contours of volcanic deposits having the same thickness. Okay. So first of all, we reconstruct what volcano did in the past, and we get a picture of its history, what it did, based on the fundamental principle of geology, which is the principle of actualism, that says that if something occurred purely from everywhere inside the caldera, we don't know where the next went. It turns out to be a complex sequence, a ash fallout. What are the areas which are, you can see this one here advancing toward Pozzuoli Harbor. This is the result of a numerical simulation, so it's solute behind their emergency plans. And the same we do with pyroclastic flows, of course. With pyroclastic flows, things are a bit more complex because we have to deal with topographies and with processes which are really very complex. And this is the result of a numerical simulation. So it's solution of equation. It's not just a cartoon. It's not a movie. It's not Walt Disney. It's a solution of equations describing the dynamics occurring inside a mixture of gas and pyroclast, which may erupt at Campi Flegrei. And whatever you see here, these are pyroclastic flows traveling along the ground. You can see this one here advancing toward the Pozzuoli Harbor, the Pozzuoli area, and clearly destroying everything here. So we can again make a number of this simulation with different size, I have to stick here, with different sizes of expected volcanic eruptions, and see what are the areas which are expected to be impacted. And as you can see here, we can obtain maps like this one. We don't only see the area.
Okay, now let's look at the real time. The geos east scene. Okay, let's see anything. Okay, it looks like the eruption may have ended finally. Whoa, I don't know what that was. Ah, the moonlight, possibly. More. Okay, guys, I'm going to bed. Actually, I'm about to go to bed.
As we also see the timing here, we see the concentration of eruptions, or at least we can deal with that. We can deal with ground started to go up. We can see it's here and here. This point here, at the beginning of last century, was explosion like this one may occur. And that's very, very dangerous. From a picture like that, we can get an image of the eruptions and the areas of dispersions and so on and so forth. And from...
Okay, so it looks like the most likely eruption to occur is either small to medium. So, like VEI4 to VEI5. There's even a 4% chance of a large, Plinian eruption. This is Plinian right here. 23.8 is Plinian. Plinian. Large is Plinian to ultra Plinian, and larger than 7 or larger, that's super volcanic. They're saying 7 to 8. There's even a 0.7% chance. That is pretty high, because that's like just
picture like that. We can get an image of the probability of having effusive, that means lava flows, or explosive, small, medium, large, or very large eruptions. And this case here says that, for example, the probability of having a large eruption will be 4% if a new eruption...
So actually, a medium eruption is more likely than effusive.
Should occur in the future. And very large, which is something comparable to a caldera-forming eruption, is less than 1% if a new eruption should occur in the future, which is not little, huh? It is important. It is a large probability, in fact. Consider that if you construct a nuclear power plant, the accepted probability of having troubles with jets must be lower than 10 to the minus 6, 1 out of 1 million. And that's 7 out of 1,000. So it's 1,000 times larger than the security parameters we will apply for a nuclear power plant. But still, if we consider that together, we see that with more than 95% probability, the eruption will be medium or smaller than that. And we start to get a picture of what we get. There is another problem with calderas. Differently from central volcanoes, they have a very clear structure with a central conduit, and the probability of having a new eruption from the central vent is very high. Instead, with the calderas, we can have an eruption nearly from everywhere inside the caldera. We don't know where the next vent will form. It depends on many factors. It could be everywhere, as all of these craters here testify. After the caldera forming eruption, we had an eruption from here, one from here, one from here, one from here, one from here, and others from other places. So with calderas, we also have a large uncertainty related to the place from where an eruption will occur. So we have to construct a probability map for vent opening, which is based again on the past history and on the investigation of the structure of the volcano, where the wake zones.
Thank you all for watching. I'm going to bed now. Let me take one more look at the real-time stuff. Yep, there's some activity here, some weak activity. Could also be a truck driving by, you know, there's more likely it is related to activity. So thank you all for watching. Good night.